chords intersect in the interior of a circle. So we're intersecting in the interior of a circle. Then the product, so that means what operation? Product is multiplication of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Okay, so over in that circle that is there for you, I have to make my own circle. Don't judge it. Let's go ahead and have two chords intersecting each other. So there's one chord. And let's make another chord intersecting it. If I wanted to find the degree of the angle, I would add the arcs, divide by 2. But we're not talking about the angles anymore, we're talking about the lengths. So I'm going to label this section of this chord. So notice how each chord is split. I'm not going to say half because it's not necessarily in half, but it's split into 2. So I'm going to label this section A. I'm going to label this section B. On the other chord, I'm going to label this section C and this section D. So what this theorem tells us is that the product of the lengths of the segments of one chord. So if I focus on the chord that has A, B on it, if I wanted to find the product of the two, I would multiply whatever my A is with whatever my B is. So AB is going to be equal to the product of the other two segments, CD. Okay, so you're multiplying the two sections together and equaling them together. That's what theorem 10.14 tells us we can do. So if we look at the example, and I know it's not drawn to scale very well, but that's okay. This is 6 and that's supposed to be 6, but we'll pretend. If I look at RT, that's one of my chords, take the product of the two pieces. So 6 times x would just be 6x. Now do the same thing for SU. 6 times 10 is going to be 60. So then I get the equation, 6x equals 60. So x is equal to 10. If I needed to plug that back in to find RT and SU, what would be the length of RT? RT. Well, RT we just said is 10. So if this is 10 and this is 6, together the whole thing, segment addition tells us it would be 10 plus 6, so 16. And SU we already knew was 16. Again, this is not drawn to scale. I did a horrible job of making this diagram. It's not always going to be the same either. They may be different. So let's look at the next one. Here we have more algebraic expressions that we need to deal with. So let's start with chord ML. The top half gives me x plus 2. The bottom half gets me x plus 1. How do we multiply a binomial times a binomial? This is a binomial, 2 terms. Not factor, foiling, right? So take your first times your first, which gets you to x squared. Your first times your last, which is going to get you to x. Your inner, so that gets you 2x. And then your last, which gets you 2. Combine these middle two terms, what do we get? X squared plus 3x plus 2. Alright, so there's the product of that chord's segments. Now let's go to the other side. Here I have chord KJ, so the product of these two is going to look like x times x plus 4. When you distribute that x, what do we get? X times x is x squared. X times 4 is 4x. So I'm going to bring that down. All right, now we got an equation. What happens to your x squareds? They cancel out. That's nice. Yeah, so then subtract your 3x over. So then we get 2 is equal to x. but I'm not done. I need to find the length of ML and the length of JK. So we just said that X is 2. So wherever I see an X, I'm going to put a 2. So the length of ML, well, the top half is 2 plus 2, so 4. The bottom half is 2 plus 1, so 3. So 4 and 3 together will make 7. Now let's do KJ. So K to N is 2, N to J is 6. 2 plus 6 makes 8. So there would be your lengths of the chords. Okay. So if two chords intersect inside a circle, then you take the product of the segments and equal them together and solve from there. All right, so that's chords inside. Then we got into what happens if your intersection is outside, and that's where it gets a little bit funkier. So, first thing we need to discuss is internal and external. In red, we have an external segment. Do you see how the external segment differs from the internal segment? Okay. So you have your external segment here. The whole entire thing is going to be your secant segment. And then down here at the bottom, we have a tangent segment. So given a diagram, the purpose of this is to be able to identify what the external part is. It's going to be the segment that's on the outside. You need to then also be able to identify the whole entire thing, secant segment. This is a tangent segment because it's only intersecting the circle at one point. Okay? So theorem 10.15 talks about if we only have secants. So if you have two secant segments that share the same endpoint outside a circle, then the product, so we're still multiplying, of the lengths of the one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So if two secant segments share the same endpoint outside a circle, then the product of the lengths of the one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. Ugh, it's a lot. So let's put it to action. So over in your circle, let's make one secant segment. And then coming off of that, make another secant segment so that they both are intersecting at the same point. I'm going to label my external of the top A, the internal B. Down on the bottom, external I'm going to make C, internal I'm going to make D. Alright, so this theorem tells us that we can take the product of the lengths of the segment, secant segment, and its external. So if we focus on the top one, my external part is A. So I'm going to take A, and I'm going to multiply it by the whole entire length. Well, the whole entire length is the sum of whatever A and B would be. And then I'm going to equal it to the same thing down the bottom. So C times, running out of space here, C plus D. So external times the whole is equal to the external times the whole is what we should be thinking in our heads. Alright, so looking at this example, I've got two secants. So let's work on the top one first. My external part is 3 times the sum of the two, which would be either x plus 3 or 3 plus x, however you want to write it, is equal to, now let's do the bottom one. My external is 4 times the sum of the two. What is 4 plus 2? 6. Good. So 4 times 6. Distribute on the left. 3 times 3 makes 9. 3 times x is 3x. 4 times 6, or 3x, there we go. 4 times 6 is 24. Now I've got a simple equation to solve. Subtract your 9 from both sides. Gets us 3x equals 15. So my final answer is x is equal to, why did I write 15 again? X is equal to 5. Okay. External times the whole is equal to external times the whole. So in a tangent, there is no internal part. So we have to think about something new. So if you have a secant and a tangent, so if a secant and a tangent segment share an endpoint outside a circle, then the product of the lengths of the secant segment and its external segment equals the square of the length of the tangent segment. So nothing is changing with my secant. What's changing is the tangent part. Okay, so in our diagram, let's make a secant segment. From that same endpoint, let's make a tangent segment. All right, let's do some labeling. So I'm going to make the external part of the secant A, internal is going to be B, and the tangent only has an external. I'm going to make that C. So what this theorem says, nothing changes with the secant. That's going to stay the same. That's still going to be external times the whole. So A times A plus B. But what happens is your tangent no longer has an internal part. So you're going to square your external part. So you need to have a product of something, so you just do the product of itself, which is the same as squaring it. Alright, so let's do the last examples here. So here I have, let's do the secant first. What's the external of my secant? 16 times the whole, which is going to be 16 plus x, is equal to the tangent, which is going to be 24 squared. Alright, so 16 times 16 is 256 plus 16x. 24 squared is 576. Subtract 256 from both sides. So that gets me 16x is equal to 0, 2, 3. So 320 divided by 16 is 20. So x is equal to 20, which is what AB would be equal to also. Okay. So let's do the last one. Is everybody good? Alright, what does my secant look like? External is 8 times, what's the length of the whole entire thing?
16 plus
18, right? 10 plus 8? Yeah. If it helps, write out that 10 plus 8, because a lot of times students will put 80 here because they think that they'll need to multiply 8 times 10, and that is not correct. So it's going to be 18 is equal to x squared. All right, 8 times 18 is 144. How do we undo a square? Square root, the square root of 144 gets us 12. Good. There it be. Any questions? Okay. So if everything is inside,